Okay, hello everyone. Welcome to another lecture of computer architecture. Today we are going to solve some sample exam questions and answer possible questions from you. So sorry for the latency, we have some infrastructure problem. The first presenter is Ataberk. He's going to solve question about DRAM latency, which was for the last year exam. So yeah, feel free to start.
Yeah, so I'll get started right ahead. So this is the DRAM latency question from last year's final exam. And it basically in the first page, it talks about the configuration of the system here, and then gives us a bunch of requests that are scheduled to the DRAM device through the memory controller. And then it also tells us at which cycle, what command was issued by the memory controller to serve these requests. So I'll get started by solving the first question immediately, and we'll go back to this information as we need to. So the first question asks, what is the size of a single row? So this, for this, we need basically this and this information. So the first one tells us physical addresses are 24 bits large. And the second bullet tells us that there are 1,000 rows per bank and 8 banks in total and in a single channel. So because we have 24 bits, and basically this also the third and the fourth bullets. The third bullet says that the DRAM is byte addressable. So every physical address will address a byte. And the most significant 3 bits of the physical memory address determines the bank, and the following 10 bits of the physical address determines the row. So we will use these 4 bullets here to solve the first question. And because the most significant 3 bits form the bank bits, that is bits 23 to 20, or is it 21? 21. And then the next 10 bits form the row address bits. That's 20 to, it should be 11, I think. And then the remaining bits, basically there are now 11 bits left in the address. So this was the bank. This is the row. These are the bytes in a row. Bytes in a row. So we will find the size of a single row from this, basically. That is 2 to the 11 bytes, because there are 11 bits left for us to address the bytes in a row. Is this clear enough? So that is also 2 kilobytes. Because, I mean, you already know 2 to the power of 10 is 124, and that's 1 kilobytes. And this is 2 to the power of 11, so multiply it by 2. Okay. Yeah, the second question asks what are the DRAM parameters here in 3 bullets, and if we can determine them. If we can determine them, the question asks for these timing parameters in nanoseconds. And to solve this question, we basically need to revisit this whole all the bullets and the requests that we executed. I'll start by basically decoding the address into bank and row bits here, the addresses of the read requests. And notice that these are ordered in decreasing age. So the first request is the oldest request in the request queue, and the last request is the youngest one. And this is important because the memory controller uses an FRFCFS scheduling policy. That means it will try to prioritize older requests, but also won't be able to issue requests if the bus is not ready to accept the command. So we'll get to that. Yeah, but let's start with decoding the address bits first. So to make this faster, I'll look at the solutions. It's on the other tab, okay. Yeah, this one. Okay. Yeah, but maybe it's here. Yeah, so these are here. So maybe I will just fetch this information. Benefits of the iPad. Or maybe not. How do I copy this? Okay, there you go. Yeah. So if you were to decode the bank and row address bits, these are what you would get for the same requests. This is important because if we're targeting the same bank, we will have different latencies. If we're targeting different banks, we will have different latencies. And the other necessary information is exactly here. So these are the commands that the memory controller executed to schedule these requests. And then basically what we do is let's look at the activate to read latency. So the first cycle we execute a pre-charge command. This has to be executed by the memory controller to serve the oldest request. And the reason for that is, again, we prioritize older requests. And we know that at the beginning of this basically timeline, assume that all banks are ready for a DRAM command. So if all banks are ready for a DRAM command, the memory controller must execute a command to serve the first request. And it executes a pre-charge command, and that means the bank 3, basically, in the beginning, had a row open. So there was a row open, row X in bank 3 that we don't know. And yeah, we were looking at activate to read latency. So this piece of information will become useful later on. But because I'm starting from the beginning, I want to let you know of this earlier. And then in cycle 1, we will send an activate command. And this will be sent to serve request 2. So this one. Why? Because we cannot immediately send an activate command after a pre-charge command. And that activate command must be for the second read request, essentially. So if we do that, then that second request activated bank 2, right? And the read command that's executed immediately after the series of the activate commands, it is also serving. It is also to serve this request that targeted bank 2. And from here, we can deduce the activate to read latency. Act to read. This is 8 cycles. And if you look at the next, the differences between next 3 pairs of activate and read commands here and here, they exactly have the same latency between them. So then activate to read latency is 8 cycles. Here, I will write 8 cycles. And we need to convert them to nanoseconds. And for that, we know the frequency. Okay, maybe I can go back to the questions here. Yeah, we know that the bus operates at 500 megahertz. So the clock period is 2 nanoseconds. And if we spend 8 cycles, it means that we spend 16 nanoseconds. Okay. And then it's activate to pre-charge latency. And for that, we will look at the latency between these two. So this one. This activate command must target the, it must be for the first request. Maybe I should clean this up a bit. Don't need these. Well, I think we need this, but row X was open in bank 3 at the beginning of the timeline. And yeah, so at cycle 4, we send an activate command. This must be the command to serve the first requests that target the bank, the third bank, this one. And we need to schedule another command to the same bank. So there's also a row conflict. That means we need to pre-charge the bank and then activate it again, activate a different row. So to do that, the memory controller will send a pre-charge command before it activates row 128 in bank 3. And this is that pre-charge command because there's nothing else to pre-charge here. And the memory controller applies open bank policy if you look at the bullets. Sorry, open row policy. That means the memory controller is not interested in closing the bank after it opens it, and there are no further requests that target that bank, that row. So the other rows remain open. The only row it needs to, the only bank it needs to close is bank 3, and that is to serve the third request. And the latency between these will give us the activate to pre-charge latency. And this is 26 cycles. And that is 52 nanoseconds because our clock period is 2 nanoseconds. And finally, we have pre-charge to activate. And for that, you can look at these two, the difference between these two commands, and that is 4 cycles, because we pre-charge the first bank. And then, so there are two ways to basically understand this. Two things to look at to understand this. The first one is the difference between these two commands, the pre-charge at cycle 0 and the activate at cycle 4. And the difference is 4. And if you look at here, it's the same. We pre-charged bank 3 and we opened row 128 in that same bank. And we spent 4 cycles again. So this must be the pre-charge to activate latency. And 4 cycles is exactly 8 nanoseconds because, again, clock period is 2 nanoseconds. Any questions here? Yes. This one. This one. So if it was not targeting bank 3, let's say, we would expect it to be scheduled here. There's no reason to expect it to be scheduled at cycle 4, basically. So what I'm trying to say is we know that the pre-charge in the first cycle pre-charged bank 3. And if there is a timing constraint that's, let's say, larger than 3 cycles, which is like apparent here, right? Then the activate command that comes after that many cycles should target the same bank, essentially. So if the activate command was sent at cycle 3, we wouldn't be able to understand which one targets which. But here we assume that this is bound by a timing constraint, and that must be the pre-charge to activate latency. Because the other timing constraint here could be activate to activate latency, right? But it looks like it's 1 nanoseconds. So the memory controller would schedule it earlier if it was bound by that constraint. Okay. Yeah. What's the row buffer state? Yeah, moving on to the next question. Okay. So this question asks what's the state of the row buffer, row buffers in every bank. Basically, which rows are open in each bank. So we only know a few things. We know that bank 3 must have some row open before these requests are scheduled. So bank 3 is open. We also know that the other banks here, 2 and 5, they're closed because we didn't send any pre-charge commands before sending the activates for them. So 2 and 5 are closed. And we have no idea about the rest. And these are unknown. Yeah, any questions here? Let me double check with the answer sheet, actually. Yeah. So unknown, bank 2 is closed, bank 5 is closed, bank 3 is open, and the rest are unknown. Okay. Yeah. So the last question here is asking us what happens if you had tiered latency DRAM design in this bank. So it says assume that a bank consists of a single subarray. So we have a single subarray in the whole bank, and that subarray has a near segment and a far segment. The near segment has lower latency in all sorts of accesses, and the far segment has higher latency in accesses. So this table summarizes what changes in latencies. And what it says is basically if you're accessing a row in a near segment, your activate to read latency is now not 8 cycles, but it's 6 cycles, because this is the difference basically between. So you deduct 2 from 8 and you get the new latency. If it was targeting a far segment, now it's 8 plus 1, 9 cycles. So this table is telling us what happens to the latency of each request. And then it asks basically, yeah, if the same set of requests here, instead of 42 cycles, it took 36 cycles. So what is the TLDRAM design? What does it look like? Meaning that which are the near segment rows and which are the far segment rows. And it also tells us that the first n rows in the bank are near segment rows, and the remaining ones are far segment rows. So I think there are a few things you can do here, but I will start by assuming that all the rows here target the near segment rows, because we need to have a lower latency now. And that the only way to do it is to at least put some of the requests in the near segment, right? So let's put everything in the near segment and see what happens. That is, basically we're setting n equals 192 and see basically what happens to the new latencies. And n is 192 because, let me copy this again. Maybe I cannot copy it. Maybe it's already copied. The request that targets the row with the highest number, largest ID is 192. So if n is 192, every row accessed by these requests are in the near segment. And then what we will do, yeah, I wanted to copy this here, so yeah, paste. And then paste this one also. Copy. And yeah. Okay. So let's look at what happens when we have everything in the near segment. So these are all invalid now, except the first one. It starts at cycle 0. And well, this activate has to go at cycle 1. Again, nothing changes because there are no constraints here. Cycle 1, cycle 2. And then this activate targets the bank that was targeted by this pre-charge command. Now, if this is in the near segment, the row that the pre-charge command pre-charge was in the near segment, then the pre-charge to activate latency is 1 cycle smaller. So this should be executed at cycle 3. Does that look right? Yeah. And then we have the read command to, again, this one, to bank 2. And this is, everything is in the near segment. So this will have let me write these down. So also default latencies act to read is 8 cycles. Activate to pre-charge is 26. And pre-charge to activate By default is 4. So it was 8 before. Now, since it's in the near segment, it is 6 cycles. And 1 plus 6 is 7. So this was executed in cycle 7. This one's executed at cycle 8 because 2 plus 6 is 8, and then 9. And then we have a pre-charge. This goes to bank 3. So again, in the near segment, activate to pre-charge latency is 5 cycles smaller. It was 26 cycles before, now it's 21 cycles, and we add 21 to 3, and then we get 24. And then we have the activate command to the same bank, and this should be 3 cycles, 27. We add 6 more, and now we get 33. So this, we overshoot the latency. So we need to put some of the rows back in the near far segment. So we basically have, if everything is in the near segment, we have a latency that's lower than what the question asks us. That's why we need to put some rows in the far segment. And for that, there is one trick we can do. We don't know which row this pre-charge command targeted. So we will put that in the far segment first. So if we do that, what happens is pre-charge to activate for that segment will be two cycles larger. And because we calculated with a pre-charge to activate latency that was 1 cycle smaller than the default, now we have to make it 2 cycles larger than the default. Now we essentially added 3 more cycles to this. And how it happened was basically instead of this activate command was not now it's not executed at cycle 3, but it's executed at cycle 6. Because it's executed at cycle 6, this pre-charge command is also delayed by 3 cycles. This also gets delayed by 3 cycles, and this one gets delayed by 3 more cycles, and we hit the latency target that we had. Any questions on this? So it's basically, I tried to minimize the latency by putting everything in the near segment first. And then because I ended up with a smaller latency than what the question asked for, I put only 1 row in the far segment. And when we did that, we got the correct latency value of 36 cycles. Now we don't know what n is. We only know it's larger than 192. And row X that was open is in that range, basically. That was open in bank 3 before everything started executing. Okay, I already took a lot of time. I think we can move on if there are no questions to the next question.
So here we have a RowHammer question in 2 parts. The first part is about the attacks. The second part is about defenses. And there's some system definition here. I'd like to highlight a few things to begin. So you can see that there's no RowHammer mitigation mechanism implemented in any part of the system. And it does not implement virtual memory. So whatever address you will see in this question is just like physical addresses. And yeah, there are some other information we can just refer back to them when they're needed. And you can see some definitions of some instructions here. But these are just like self-explanatory. Basically, there's an unconditional branch, there's store, there's CL-flash, very straightforward. And I think if you look at this first program here, okay, you cannot see that. Maybe I can zoom in a little bit more like this. If you look at this first program here, you can see that, I mean, it might look familiar to you from the Philippine Bits papers presentation that Professor Mutlu did during the RowHammer lecture. So we have 2 memory accesses here, and then 2 CL-flush instructions that basically flushes the cache line back to main memory so that you hope to access main memory and hammer rows. So, okay, let's check the first question. So in the first question, we say that, okay, you have this program 1 and you run it, but you cannot observe any bit flips in the target system. and you figure out that the number of activations is much lower than what you expect. So you're shooting for like very large hammer count, but when you actually probe the memory bus and see like how many activations are being performed, you only see like a few activations going on. So what might be the problem? So that's the question. Like, so the question is asking for like two potential reasons that might cause this kind of observation. And there's definitely like more than one correct answer for this kind of question. As long as your answer makes sense, you will get the grade. So does anybody want to try? Sure. Yes, but I think you need to elaborate more. In the same row, yes. That can be one reason, right? You can, so to clarify for everyone, so you have your bank, you have your rows here. Let's say this is bank and this is your row. If one address is hidden here and the other address is hidden here, so every time you access the memory, you will hit the same row. So the content of the row is going to be in the row buffer here, and you will never access the row actually. I mean, you will access it one, two times, and then you will just service other accesses from the row buffer. So that can be one reason. What about the second reason? So similar to this, we can also have an address mapping that actually puts this second piece of data into another bank. So in that case, as you know, each bank has their own row buffer. Once you access this address, for example, you will be accessing this row buffer. Once you access this address, you will be accessing this row buffer. So it's also, again, a lot of row buffer hits, and there's no hammering kind of access pattern going on. So another thing can be you're relying on CL flush instructions here to flush your cache lines to the main memory. But maybe in that particular system you're using, the CL flush instructions are not allowed in the user level. Maybe they're just ignored. So that can be also the case. And yeah, we have a few different answers here. You can check later, I think. Yeah. So yeah, as long as you provide like two reasons that makes sense, it's okay. Okay, so in the second part of the question, second part of the first part actually. So it's like, yeah, again about the attack 2.1b. So we have three different programs in this question, and we observe that only two of these programs can induce RowHammer bit flips, but the third one cannot. And so the question is asking like which program segment is the one that does not induce RowHammer bit flips. So again, we have, yeah, these codes here, very similar to the one that you see earlier. So here, we are accessing different addresses in these three programs, if you notice. So we can just focus on these addresses and see what is different, right? So here, so this is in hexadecimal formats, right? So we need to convert them to binary format and see like which address bits they have. And for that, we also need to check a few system configurations, basically. But from the previous question, from your answer, for example, we know that for a program to induce RowHammer bit flips, these stores should access different rows in the same bank, right? So if they access different banks, it doesn't make sense. If they access the same row, it doesn't make sense. So let's check this out. So in the question, it says your physical memory address is 16 bits, and you have 2 channels, 4 banks per channel, and 64 rows per bank. So since you have 2 channels and 4 banks per channel, you can actually identify a bank using 3 bits, right? Like 1 bit for the channel and 2 bits for the banks. So you will look at like 3 bits in total, and then it will give you the bank ID, basically. So here, I'm just showing the solution because I don't want to take a lot of your time. So this is just binary representation of these hexadecimal addresses here next to them. And if you check actually which bits are common, which bits are not common across these 2 addresses in like for each program, you see that so these addresses are common here, right? So the other bits are different from each other. And similarly, for program 2B, these addresses are common. And for program 2C, these addresses are common. So since we know that in a successful RowHammer attack, these common bits, I mean, the bank ID should be common, right? We can say that. So since these 3 bits, if these 3 bits represent which bank we're going, which bank these addresses are mapped to, we can see that. Okay, so these this program 2B and program 2C can be sending the two requests to the same bank. While so if you look at these bits, for example, so this is based on an assumption, and you just build confidence on your assumption, right? So we just assume that these 3 bits identify the bank ID, and for 2B and 2C, we see that these bits are common across these 2 addresses, and therefore they would be addressed in the same bank. But if we look at 2A, so these bits are not identical. So these 2 addresses can be addressed in different banks. So that's one explanation, right? You can just say, okay, these 3 bits are bank IDs, and that's why 2A doesn't work. So if you come up with an alternative solution, it will also be accepted, as I said earlier. Okay, so about RowHammer defenses. So here there's a lot of text, but I'll try summarizing it. So here, what we do is actually, we observe that when we run some workload on some system, we observe some bit flips. And when we investigate like why this happens, we see a correlation of like, when we have more activations, I mean, in a certain access pattern, basically, we observe bit flips, and this certain access pattern happens to be activating a row A many times. So different from the first question, here we have a mechanism that actually tries mitigating or defending against RowHammer. So these are the specifications of the system and the defense mechanism. So when we look at the DRAM chips RowHammer vulnerability level, we see that a row needs to be activated at least 20,000 times. So this is your RowHammer threshold. So to induce a bit flip, you need to activate 20,000 times. And is there a question? Okay, I think Banu doesn't have a question. Okay, do you have? Okay. So, okay, so when we look at our RowHammer defense mechanism, the behavior comes like this. Whenever a row X is activated 4096 times, it actually triggers a defense action that actually sends row activation commands to the row addresses x-1 and x+1. And also from the DRAM chips characterization, we know that blast radius is 1. So meaning that when you hammer a row, you induce bit flips only in the adjacent rows. not the other rows. So, and when we look at the memory access pattern, actually, this memory access pattern activates row A 30,000 times. So this is definitely larger than 20,000 times, right? In a 32 millisecond time window. So I think from the specification, we can see that it's, I mean, in 32 millisecond, the victim rows are not refreshed. So that's there. And also, during these activations, the defense mechanism activates row A-1 and A+1 once every 4K activations targeting row A, right? So, okay, you activate row A 30,000 times, but after every 4,000 activations, you actually send an activation command targeting A-1 and A+1. So the overall hammer count you observe shouldn't actually exceed 20,000 times, but still you observe some bit flips. So what would be the reason? So, okay. Any guesses? Go ahead. It's very close, yeah. You're getting there. Yes, I think terminology is a little bit different over there. So since the system doesn't have virtual memory address space, I mean, when you say virtual to physical, it's some translation in the operating system level, right? Here we just say actually it's a mapping that happens in DRAM. So it's just like in DRAM row address mapping. So the reason is you send an activation command to A-1 and A+1, but those are called logical addresses, and they might not be actually, they might be mapped to some different rows in the physical layout. So you're not actually refreshing the victims, as you said, and therefore you observe bit flips. So the second part of this question is asking, if instead of this defense mechanism, we implement para, would that help? We're just like speculating here, right? Hypothetical case. So instead of like, do you guys remember para? Okay. I'll just give a reminder anyways. So when you send an activation, para observes these row activations, and after every activation, it just performs a probabilistic process, and with a low probability, it sends activations to X-1 and X+1, but not based on some counter value. So here, the different thing between this defense mechanism and para is para will not track these activation count and trigger it when it reaches to 4,000, but it will probabilistically trigger it. So would replacing this with para solve your problem? The answer is no, because para would also activate these rows that can be physically mapped to some different rows. So it wouldn't solve our problem. And the last part of the question is, would implementing block hammer? So this is the lecture that it was discussed in last year. I think it is something different this year. In memory controllers, instead of this defined defense mechanism, would it solve the problem? So as a reminder, block hammer was not sending activations to the victim rows. Instead, it was throttling the activations targeting the aggressor row. So basically, it guarantees that no row will be activated more than 20,000 times. So since the activation count is limited in that way, even though this A-1, A+1, X-1, X+1 are mapped to different rows, it doesn't matter for block hammer. It would save the day, basically. And that's the answer, yes. And that's the end of second question.
Okay, so this is a processing memory question and tells you that you have two applications that you want to accelerate, application 1 and application 2. And then also give you some information about the system, that baseline CPU system and a processing memory system. We are going to get back to that here at some point. And the first part asks you what is the execution time of both of the applications when you're executing that in the baseline CPU, and you don't need to account for the time for these first few instructions over here. So it's just the time of the loop. Okay, and here it tells you that the CPU is a single issue in all the processor. All loads and stores are serialized, gives you the frequency of the CPU, and also tells you the time for arithmetic operations. Jumps is 1 cycle. If you have to do a complex operation, it takes 50 cycles. And load and stores are 4 bytes, loads 4 bytes of data. So if you look at this first loop here, so the execution time is going to be equal to the number of cycles that you're going to execute this loop for, times the latency of a single iteration. So let's say which one of those parameters next. So you can see the branch here for this loop. It's for 1 billion iterations. So you're going to execute this loop 1 billion times. So this is 10 to the 9. And then you basically just need to count, because the processor is in order and everything is serialized. You just count how many memory operations that you have. You have 2 loads here and 1 store here. So we have 3 memory operations. You have 1 multiplication, 1 addition, and 1 increment. All of them are simple arithmetic operations as defined here. So you have 1, 2, 3 simple arithmetic operations. And you have branch, yes, the branch operation. And if you go back to the latencies here, the latency of the memory operation is 100 cycles. So it's going to be, let me move this here. Oh, it's in Turkish. I don't know. How do I copy this? Maybe I... really good. So it's going to be it's going to be 3 times 100 plus 3 times the latency of the other one was 1 cycle, 3 times 1, and then the other one is the latency of a branch was also 1 cycle, so 1 times 1. So this is you can do the math. Usually when I'm grading, I don't care so much about if the math is correct or not. So as long as if you give me the equation correctly, I will give you the points. But if you try to do the math and then give me a wrong answer, I'm going to remove some points because I have to go to the math then. So it's better just leave it as it is, so it's safer. Okay, so the second application, you do the same. You check here. This is a bit different. If you look at the branch operation here, the increment for this branch is increments of 2. So this is going to actually operate off, is going to execute. It's going to execute to half of 1 billion times. And then again, you multiply by the latency of a single operation, of a single iteration. So here we have 1, 2, where is this store? 3, multiply, so here, 3 memory operations plus 1, 2, 3, 4 simple operation arithmetics plus my right is discussed. Plus one complex operation, this is square, and this says that it takes 50 simple operations, which is 1 cycle, so it's 50 cycles. So one complex, and this one, and the branch. So this is going to be equal to 10 to the 9 over 2 times 3 times 100 plus 4 times 1 plus 1 times 50 plus 1 times 1. So there is any question here? Okay, great. So now we are going to implement a processing-in-memory accelerator for this architecture. And here it gives you some of the limitations of the processing-in-memory architecture that you are going to design. So you're saying here that you're going to design an accelerator in the logic layer of a 3D stack memory, which can provide your accelerator 4 gigabytes per second of memory bandwidth. But at the same time, you have an area limitation, an area envelope for you to design an accelerator of 100 millimeters square. And the clock frequency of the accelerator is going to, because it's in DRAM, is going to be lower than in the CPU. So it's going to be 1/10 of what the baseline CPU can run. And the important part here is that the accelerator is going to consist of multiple processing elements, and each processing element is going to have several functional units. And then it gives you a table here with the functional units that you have available for you to execute and some description of them. And then the latency that they are going to take in cycles and also the area that they are going to occupy. And then it's saying here that the process element is going to execute the same computation as the entire body of the loop. So there's no pipeline, you execute every single loop at one step of in the processing element. And they say here, therefore, if you have any processing elements, any iterations of the loop are executed in parallel. So as many processing elements you have, it means that is the parallelism that you can extract from the loops. The loop iterations are executed on the processing elements as described by the compiler. It's not that important. And it also says here that you can reuse functional units inside the processing element in case there is no data dependence for that particular operation that you want to accelerate. So you say here, 2 processing functional units can be executed in parallel if there is no dependency between the operands. So you're going to design this accelerator with the maximum number of processing elements as possible that fits in the power and the area budget that you have for the pin accelerator. And then the first part asks you what is the area of the configuration of your processing accelerator that provides the highest performance for each application fitting the processing-in-memory budget. Show your work. So usually if you see a processing memory question in the paper, in the exam, I designed it. And if there is a code like this, probably you're going to have to do a data flow graph to do some computation because I really like data flow graphs. So from the start, I would already start drawing it. You don't need, you can ignore this first part here. We are all interested in the loops. How you do this? So the first, you basically need to figure out the dependencies that you have in this code here. If you get it correctly, you're going to get the rest of all of the equations correctly, probably. So the first operation that you have is a load, and this load produces R4, and then you have another load here that does not depend on the previous one, and it's going to produce R5, and then you have a multiplication operation that is going to depend on R4 and a constant. So this is your multi operation, and going to produce R6. And then you have add operations that's going to depend on R6 and R5. So here is an add operation. And then you're going to have a store operation of this R6. So here we have, so here is R6. And this is a store operation. And then you have the increment. The increment, so the previous operation, the store, still depends on the value of the increment. So there is, since there is no register renaming or alias that you can do here, you need to wait to increment the variable, otherwise you're going to store the data in a wrong position. So you only can do the inc after, even though there is no this is a false dependency. We need to respect that because there is no way to fix it. The question does not tell you that you should fix it. So you have to do the inc here, and then you're going to give R3, and then you have the branch operation. So this is the data flow graph for this particular application here. And now you're going to design the accelerator for this data flow graph. Well, what did I do? Copy the wrong thing. I lost my data flow graph. I don't know what I did. I pasted the third one. What does it mean? Ah, it's back. I said seal. It's not that one. Cut is which one? Ah, is this one?
The first one is.
Thanks. Okay, great. Ah, yeah, this is true, but it's fine. Let's continue here. So this is your data flow graph for this accelerator. So in parallel, actually, you can only have this load instructions here. Everything else is serialized. So you can have, let's design it for a single processing element first. Let's say that here is your processing element that you're going to design. And then you're going to just replicate that for the other, but depending on the area here, just duplicate that as much as you can to parallelize the loop or to open the loop. So here you're going to have two, because you can do any then in parallel, you're going to have two load units. And then for all of the other arithmetic units, they are also realized. So the multiplication, the addition is going to happen only after the multiplication, and the same for the increment. So you can have a single ILU here, because again, it's written here that they can be reused. I think is the other part actually. And then this store, so you already covered this operation here, this one, this one, this one, this one. This store can be reused with these loads because those are both load and store units actually. Yes? Yes?
Wouldn't it be better to parallelize the load with the and don't use the second load store?
No, but you cannot parallelize the. What do you mean? There is a data dependence between the two? Yeah. So you do, oopsie. You do first the first two loads. So here there is a data. Yeah. So so you do the first two loads and then you do the move. You cannot move this move earlier because of the dependency.
Is there between the right load and the multiplication?
There is no dependence.
Then you could just move this like 1 times load later, and then you don't need the other load stored.
But then you're going to serialize loads. You're going to increase. You're going to.
No, you're
You're saying that. Okay, I understood what you're saying. You're saying that you do you can do a load, and then you do the move, and then here you do the load again, and then you do them, and then you use only a single load unit. You could do that, but then there is going to come to the next question, because at the same time, since this is a processing memory engine, you want to maximize the bandwidth utilization of your memory device as much as you can. And the bandwidth utilization that you're going to be able to achieve here, since the only parallelization that you're going to have is those load units, depends on how many load units you have. So it's quite important to do as many load operations as possible in parallel, so you can fit you can fully optimize the bandwidth of your DRAM. But yeah, it's possible. Will be another solution. I don't know actually if the performance would be better. I don't think it would actually.
You need one less.
Yeah. But as you're going to see, it's going to give you exactly the area of the area budget that you got before. So I think it's going to be you're going to use less area if you do that. But then you cannot put another processing element for you to do the computation. So the answer that is going to give you is 25 processing element units. If you save one unit for a single processing element array, you can still not add another one. It's not going to give you 26 processing element units because of the total area. So you're just, okay, you're saving the area, but you're not using any, you could exploit more parallelism if you use that extra area that is not used to do anything else, actually. It's just there. But anyway, yeah, it's the intention, yes, you could do that. Okay. So the LU here, and the branch unit that you are missing. And then that is done. So all of those 4 here. So, and then you check the area of each one of them. So if I'm not mistaken, the area is 1. So the area of a single processing element array is 4 limit square. Your power budget is 100 millimeters squared. And then you divide by 4. You can have 25 of those ones. So the area that you're going to utilize in the end is going to be 5 times 4 millimeter squares, which is 100 millimeter squared solution. Is there a question? Can you fit 33? If I do that, let me do the calculation. So it's going to be, it's 3 actually, 33.
And then you could perform 33.
Yes. No, can you fit 30? Yeah, you can fit 33 actually. Oh, this is good. Anyway, completely changed the solution, but it's fine. Yeah, I guess, yes, you could further optimize this if it's 33. Yeah, it's true. Anyway, I'm going to continue with 25 just because all of the other things are 25, but good that you guys found a better solution. And then the next one is pretty much the same. You do the first load. Then you produce R5. In the second load, you produce R6. And then you do a subtraction. Then you produce R5. And then a multi operation, also R5. And then addition with needs R4. It was before. And then this produce R4, then you do a square operation, then the store, finally branch, no, sorry, int and branch. So pretty much the same here. This time around, you cannot do that because of there is no place to put the other load. But anyway, this you need the 2 load units. So discover this one and this one. Then you have the arithmetic unit, the LU, the branch unit here, and also the square root units. So this is going to take 1 millimeter square, 1 millimeter square, 1 millimeter square. I think the other one is 30. See one here. So the total area of this guy here is 24 millimeter squares. And if you do the calculation, not miss wrong, it should be this, and this gives you only 2 of those units. And then, so it means that the area that you're going to use is 34 times 2, 68 millimeters square. Okay, any question? Okay. And then asks you, are the processing accelerator obtained in B capable of fully utilize the memory bandwidth of the 3D stack memory provided in application 1 and application 2? So the memory that you have gives you 40 gigabytes per second of bandwidth, right? This means that you load 40 bytes in 1 nanosecond, or since the frequency of the process memory unit is 10 times lower, so this means that you can load 400. You need to load 400 bytes in 1 cycle of your processing memory engine to fully utilize the bandwidth of your device, of your memory device. The accelerator that we designed before, we can load the maximum of each load operation is 4 bytes. And in a single processing element unit, you can, because I designed with the 2 on in parallel, so you can load 2 operations at the same time. And you have 25 units. So it means that this accelerator can load 8 times 25, which is, is 50. Yeah, this is smaller, which is smaller than the other one, right? So it means that this accelerator cannot fully leverage the bandwidth that you can provide for the pin unit, for the 3D stack unit. And it's pretty much the same thing here. 40 bytes that you need to, should be your target. And then you check how many loads you can do in parallel. Again, 2. So it's pretty much the same, it's the same math. So the answer is no, because of the same reason. Okay, so what is the speed up of the processing accelerator compared to the execution of the CPU baseline? Show your work. So you basically need to figure out the execution time of your pin accelerator. So here is going to be the latency of a single iteration here is going to be 1 cycle here. So it's going to be 1 cycle, plus 1 cycle here, another cycle here, another cycle here. So 1, 2, 3, 4, 5, 7. So it's going to take 7 cycles. And we open the loop 25 times, right? So times 25 iterations. So it's going to, I'm not going to make them do the math. And then the cycle time is the CPU was 1 nanosecond, and this one is 10 times lower, right? So it's going to be 10 nanoseconds. So this is going to be the execution time. And then you basically divide the time that you calculate before. Yes, the time that you calculate before for the CPU. This one here. Yes. Just a sec. By this one. I'm forgetting. I'm forgetting something. This is not correct. Yeah, I forget the iterations. Yes. Divide by 25. Yeah. So now it's correct. Don't try, please. Yeah, exactly. So for just write the equation really clearly, which is one of the things, like not as clear, like this is disgusting. So yeah. Don't try. It's much easier to grade because then you just see the terms and like go see it. Sometimes it's going to ask like, oh, can you provide speedups in a particular configuration? So you have to have more or less the idea of the order of magnitude of one of the other to see if it's going to provide speedup or not. But then you can see more or less, don't need to fully calculate to get the end number. As long as, and usually the numbers are big enough that you can clearly see there is like one order of magnitude difference from one to the other, and then you can infer which one is bigger, and then you can just say, one is faster than the other, and then you put the equation there. Girai, I locked this screen by mistake.
Trying to share to them.
Okay, thanks, Girai. Okay, great. So, because of time, it's best this divided by this one. Did you guys understood more or less how it was done? Okay, so the other one is pretty much the same thing. You come here and you count. It's going to take one cycle here, one cycle here, one cycle here, one cycle here, one cycle here. The cycle of the square root, I think, is 70. Yeah. One cycle here, one cycle here, one cycle here. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. 8 times 7 cycles. Cycles times the latency times it was 10 to the 9 divide by 2 divide by 2 again, right? Because the iterations here was 500 million. Yeah, was 500 million iterations, and we opened the loop 2 times, right? Here. No, where it is. Here, we opened the loop 2 times, right? So you parallel the loop twice. So it's going to be, this is going to be the execution time, and then you divide by the other one for the CPU. So speed up. Yes, that's it. Is there any question? Okay, so that's all.
I'm going to discuss the fourth question, the memory-X patterns and interference. This is a question that it's not so hard to solve, but you need to have more critical thinking rather than doing calculations. So let's start with the definitions here. So you can see a graph with some vertices and a compression format. We don't really care about this. We just care about some specific properties of the application, of application 1. So that's why I'm not going to dig deeper into that. So the application 1 essentially is page rank, okay? And the most important, one of the most important properties is this one, that every value of the data structure is a 4-byte value. It's an integer. That's important so that we can do our calculations. So let's dive into the application 1. So first, as we can see here, we have
5 allocations, right? The old rank, the destination vertices, the weight, and the source. And different data structures have different sizes. So the old rank depends on the number of vertices, the rank on the number of vertices, destination data structure on the number of edges, the weight data structure on the number of edges, and the source data structure on the number of vertices. So what the application is doing at the beginning, it's doing some initializations for the data structures. And then we are iterating on top of the vertices. So as you can see here, the I is iterating on top of the vertices of the graph. Let's say we have 100 vertices, we will do 100 loops. Then what do? We need to find out the number of neighbors for each one of the vertices, and we need to access the source data structure, right? So using the source of I, we first find out how many neighbors does this vertex have. So then we need to iterate on top of the neighbors. We need to iterate on top of the neighbors. So when we iterate on top of each one of the neighbors, we first need to do 2 reads. So our first read was the source of I, right? So the next read was the weight. We need to read the weight at the edge, right? And as you can see, the edge is a counter that progresses after its nested loop. So I will say why this is important in the first question. The next one is the old rank, which we access for every vertex. It depends on the I. The next one that we need to read is the destination at the edge. And then the next one is the rank using the result of the destination at the edge, right? So as you can see, how many instructions do we have? Source, weight, old rank, destination, and rank. So we have 5 memory accesses in total, right? So then the question gives us the number of the configuration of the system. So the system consists of a single core CPU and a single DRAM channel with 4 banks. All memory requests are served by DRAM. There are no caches in the system. Memory requests are serialized. What does that mean? The memory requests do not overlap, and CPU stalls until data arrives. So everything depends on memory. The processor requests data from DRAM only to access these 5 data structures used in the application 1. There is no memory access reordering. And what does that mean? The way I described how the accesses are happening, this is going to happen in DRAM. This is how the requests are going to be sent in DRAM. For example, here we access first source 0, weight 0, old rank 0, destination 0, and then the rank with the result of the destination 0. And yes, and we assume here that we have a single request for reading and writing to the rank. So all the data structures are aligned at the start of a bank row. All the data structures are mapped in consecutive memory locations in each bank. If we have a 4 kilobyte DRAM row size, then the rank 0 up to rank 1024, assuming that each element has 4 bytes, is stored in row 0. The rank 124 up to 2047 in row 1, etc. So the latency of activating a row is 100 cycles. This will be needed with some calculations. Latency of reading the data from an activated row is 16 cycles. Latency of writing data to an activated row 20. Recharging 80. The DRAM bus width is 4 bytes. We send and receive 4 bytes. Yes, the latency of transferring these 4 bytes is 4 cycles, the latency of the bus. The row buffer size is 2 kilobytes, with each bank size being 64 megabytes. The bank size here doesn't matter, it's like extremely big, so that we don't have any issues with data that do not fit in the banks. We have an open page row buffer policy. Can someone remind me what's the open page row buffer policy? Or I can describe it. Okay. So the open page row buffer policy means that whenever we activate a row, we do not close it. The memory controller does not close the row, doesn't precharge it. It's left open, so because we may have some locality from the next access, and we might hit in the next row when we access the next row. We have a first come, first served scheduling policy, and all the DRAM banks are initially precharged. So let's go to the first question. The first question says, identify the memory access pattern. It's either random, irregular, which is random, irregular, strided, or stream. Stream means we have a stride equals to 1. Strided means we have a stride which is different than 1. And random irregular means that we cannot describe whether it's stream or strided. for each one of the data structures used in the application, and we need to reason about the answer, right? So, does someone want to try? So first we have the source. How many times how is the source accessed? So for every external loop, we iterate over I for all the vertices, we access source of I. So what's the data pattern for source? You can say. Correct. So the source is a stream. Okay, then let's say the old rank. Correct, it's a stream. The weight. What is a stream? Oh, it is a stream. It is a stream, yes. The destination, it depends on the edge, is also a stream. And which is the key here? Then the problematic one, it's the rank. Because the rank depends on the value of the destination, right? So when there is this sort of dependency, the data dependency, that loading a data structure depends on loading another one, it usually is a random or irregular memory access, right? Because we depend on the values on the content of another data structure. Okay, so right now we're going to study how, yes. You can say that in the application, like its source, we access the external loop source of 0, 1, 2, 3, etc. Right? The basic thing here is that for the rank, you explain why it is irregular or random, because it depends on another data structure. Okay. The second question is about the memory interference, how these data structures interfere in the main memory. So we consider a case where the data structure rank and DST are mapped in bank 0. So we have bank 0 here. We have 4 banks in the system, right? We have bank 0, and inside bank 0 we have rank and DST. So here it's rank and DST. Weight is mapped in bank 1. So the full bank 1 has weight, I say W. Bank 2 has old rank, and bank 3 has source. It says right now, calculate the number of row buffer conflicts after executing up 1 using an input graph with 2 to the power of 19 vertices and 2 to the power of 22 edges. So first, what is row buffer conflict? Everyone knows what that is. We all know what that is. So a row buffer conflict happens when we have an activated row, and for some reason the memory controller sends a request and it needs to pre-charge this row and activate another row. This is called a conflict. Do not do the mistake of thinking that a conflict is a miss. It's not the same as a miss. Miss means that we have a pre-charged row and then we need to activate a row. This is a miss. This is not a conflict. So how do you do this calculation, right? So the most tricky part here is that the bank 0 has rank and DST inside it. How many times will rank and DST be accessed? So DST will be, it's a stream, right? So, and as we can see, the DST will be accessed once for every edge. So it will be accessed 2 to the power of 22 times. And how many will the rank, how many times will the rank be accessed? Same as the DST, because it's accessed for every neighbor of every vertex, which means 2 to the power of 22 times. So we know for sure that this will be accessed 2 to the power of 22 times each. And we know that they're in the same bank. So we activate one row for one. And then what happens? We need to close it, access the other one, access the other data structure. And this happens interchangeably. As we showed before, we first access the DST0 and then the rank of DST0. So in the next iteration, what do we need to access? DST1 and then rank DST1. Yes. The edge is increased, right? Yeah. Yeah, but it's for every edge. So what will happen in this scenario in rank 0, right? We will need to do 2 to the power of 22 conflicts when we access the destination, and 2 to the power of 22 conflicts when we access the rank. So let's go to the weights in the other 3 scenarios, which have, it's the same thing, it's in common. What's the difference here? We need to activate another row and have a conflict only when the row finishes. When the row finishes and we need to go to the next row, then we need to activate another row, right? What does that depend on? The number of values we read from each row. Which is the number of values we read from each row? Each row it's 2 kilobytes, and we read every time 4 bytes. So it's 2 to the power of 11 divided by 2 to the power of 2, which is 2 to the power of 9. So every 2 to the power of 9 times, for every 2 to the power of 9 reads, we need to have a row buffer conflict. And how many reads are we going to do? 2 to the power of 22 for the, let me see, 2 to the power of 22 for the weight. So 2 to the power of 22 reads for the weight divided by 2 to the power of 11, which is divided with 2 to the power of 2, which is 2 to the power of 22 divided by 2 to the power of 9. Then for this one, for the old rank, how many accesses do we need to do? We need to do less accesses here. We need to access it. This is a tricky one, I guess. It depends on the external loop. So we need to access it to the power of 19 times because it depends on the number of vertices, right? Yes, it's stored in a register, this one, for example, because in the internal loop, you use it, right? So it's 2 to the power of 19, again, divided by 2 to the power of 11, divided by 2 to the power of 2, because we have 4 byte values. And for the source, we access it, yes, 2 to the power of, yes, 19, divided by 2 to the power of 11, divided by 2, second one. Okay. So what is wrong here? Like, let's say that you give this answer. Why is this answer wrong? Because there is a small mistake in that. Like if you leave it like this, there is a small mistake. This is the total accuracy, that's correct. Can anyone think of the mistake? There needs to be a minus. Okay, in the beginning, all the banks are pre-charged, so you don't have a conflict, right? So it's -4. Okay, so don't be careful with these mistakes. Because we have 4 banks, all the banks are pre-charged in the beginning, so we don't have these 4 conflicts in the beginning. So let's go to the second question. We need to calculate the number. Does anyone have any question on this? No. Okay. We need to calculate the number of cycles that the processor stalls while waiting for data from memory when executing up1 using an input graph, which is the same input graph to the power of 19 vertices, to the power of 22 edges, that leads to exactly 2 to the power of 20 row buffer conflicts. How are we going to think about that right now? So the way I would do it is first, what we need to calculate is the reads and the writes. That's the important part, because how do we calculate the total formula? It's like conflicts. We pay a cost for the conflicts if there are, and then we need to pay the cost for the reads and the writes to the memory, right? So first we need to see how many reads and writes happening at the same time. So we have reads and writes. So we have 2 to the power of 22 for the rank, because it happens for every edge. We have 2 to the power of 22 for the DST, 2 to the power of 22 for the weight, 2 to the power of 22 for the old rank. So here, for the old rank, if you use the number 2 to the power of 19 or 2 to the power of 22, it doesn't matter. I will give the full points. I would give the full points because someone can say what Liana said, that there is a register, there is no register. So it's the same thing for me. It doesn't matter. Because even though we access it using the same value for the internal loop, if someone says, okay, we'll use it 2 to the power of 19 times, I would give the points. It's the same thing. So 2 to the power of 22 times for the old rank, and 2 to the power of 19 times for the source. So what happens during a row buffer conflict, right? So what is the formula? So the formula for calculating the cycles is first the cost of row buffer conflicts, how much time it takes to serve the row buffer conflicts. So we have row buffer conflicts multiplied by what? So we first need to pre-charge in a row buffer conflict, and then we need to activate a row because we have an open row policy, right? So it's 80 plus 100 cycles, 80 for the pre-charge, 100 for the activate. And then in the case of a row miss, the only thing we need to do is we need to activate the row. So we need to, yes? So we need to pay for 100 cycles. In the case of a miss, we need to pay for 100 cycles, yes. Okay, so, and then in the case of reads writes, how much time does it take to read and write the data from memory? If you read from the row buffer, if you read the definitions in the beginning, it's 16 cycles for the reads. So you have here for the reads, it's 16 cycles, right? Why is this plus 4? We need to read and then transfer the data, right? So we need 4 extra cycles. For the writes, how many do we need? 20 to write the data and 4 to transfer the data. 20 plus 4. So the row buffers are given. The row buffer conflicts are given to the power of 20. The row buffer misses, it's 4, the initial ones. So this equals 4. The reads, we calculated them in the beginning, and the writes, we also calculated them in the beginning. And you leave it like that. You don't need to do any calculation. I don't mind at all. Like I just need the formula so with all the numbers so that you can calculate the total number of cycles. Does anyone have any question? So have this in mind. It's usually this sort of question, like you need to calculate the row buffer conflicts, row buffer misses, latency for the reads, latency for the writes, and come up with total latency. So for the last question, it's a qualitative question. So we need to replace here the DRAM of the previously used system with 2 different DRAM devices, NDRAM, normal DRAM, and RL DRAM, reduced latency DRAM. Each one of these devices is connected to the processor using a separate channel. NDRAM is the one that we used before. And RL DRAM operates with half the internal latency. For example, pre-charge, activate, read-write latencies are half of NDRAM, but has only 1 bank compared to the 4 banks of the previous DRAM. And it says here, given this system, how would you place the data structures of UP1 across NDRAM and RL DRAM to maximize performance? So given that the reduced latency DRAM has only 1 bank, which data structure would you place in that bank, assuming that the data structure fits inside the bank? Does anyone have any idea? You need to go back to the first question to figure this out. Yes.
the irregular access?
Correct. Correct. The irregular accessed one, we know that it will incur many buffer conflicts, even if it's on its own inside the bank. So what we would like ideally is to access it with much lower latency. So what we would do, let's say that this is the processor, right? The core, let's say, and we have these two channels, and here we have RL DRAM, and here we have N DRAM. So here we would place the rank, as correctly mentioned. We would send the request, we would have a benefit from a lower latency, and in the other 4 banks, we would place each one of the other four data structures of the application, which is, okay, this is an easier, let's say, qualitative question. Does anyone have any questions on that?
So the first type of like the 5.1 is like about true false questions, and the answers are already given, but I would like to discuss why some of the answers are wrong. So the first one is data is written to a PCM by injecting current to change the magnetic polarity of the phase change material. So it's true that we inject current to change the phase change material, but we change the like the optical reflexivity instead of the magnetic polarity, and then STT-MRAM chain like is used to is the technology that is like working by changing the magnetic polarity. So this one is false. The second one is PCM can be denser than DRAM, while DRAM is faster and more durable than PCM. Hence, there's an opportunity to benefit from both DRAM and PCM by building a hybrid DRAM PCM memory systems, which is true. I think like there was some papers explained in the lecture for that one. The third one is multi-level cell NVM has lower latency and energy consumption than single level NVM. And then in this one, both are actually wrong. It requires both higher latency and higher energy consumption for that. The fourth one is NVM has lower endurance than DRAM because writes to NVM take much longer. So this is false, but it's also again partially correct because NVM has lower endurance, but the reason is not because writes take much longer, but when you're writing, you just apply very high temperature, so you destroy the cell structure a bit. And the fifth one is it takes the same energy to write 00 as to write 11 into the multi-level cell PCM cell, which is wrong because 11 has the like least resistance, and then 00 has the highest resistance, and you apply different temperature, and then the duration of the temperature is also different when you want to write these two different values. So the second part is about like computing some things, and this is like a long explanation that I will not go through all of it, but there are some important numbers that you should take from here. The first one is we know that memory cell fails after 10 to the 7 writes, which is important to remember. And then it says that it has like a perfect very leveling scheme so that like writes are equally distributed. And then our goal is to estimate the lifetime of PCM, right? So what it says is that the student estimated already, and then the lifetime is around 3 years. So it says 3 things about like how the instructions are executed. The first thing is that processor is in order, there's no memory level parallelism, and there's like write requests are fully serialized, meaning that all operations are fully serialized, basically. And then it says like the total latency of a write is like sending memory request from processor to memory controller to PCM, and also a write part of the PCM, which is here. So we have like the total latency of one write is going to be the summation of these 3 numbers. And then it says like the read or write granularity is like 64 bytes. Oops. And then the last thing is that it adopts a quad level technique. So once we have all these results, like figured out, extracted from this explanation, we can solve the problem. So the problem is the question is asking for us to calculate the capacity of PCM that student uses. And it says like we can approximate 3 years by 10 to the 17 nanoseconds. So we know that we have to write 10 to the 7 writes to each cell for all cells to be worn out. And then we know that like each write is going to be 64 byte granularity, so which is like 2 to the 9 bits. And then so the total number of writes you need is going to be 10 to the 7 times capacity over 2 to the 9, because each write is going to be like writing this much portion of the memory, and then you need to write each portion of the memory that much time. And then the total write latency is the three numbers we found above, which is like 8 plus 13 plus 43, which is equal to 64 nanosecond. So we know that the total duration is 10 to the 17 nanosecond, which should be equal to the number of memory positions that you should send writes to, which is capacity over 2 to the 9 bits. Sorry for my terrible writing. And then the number of writes you should send for each position of the memory, and then the time it requires for one write in total, which is 64 nanosecond. And then you should solve for the capacity, which is going to be 8 times 10 to the 10. Any questions? Guess that was clear. So the next part is about like improving the lifetime of PCM cells, and we need to extract now our new numbers. It says like the cells endurance is increased by a factor of 10, and then now we have not a multi-level cell but like single level cell. It says like the lifetime is increased by 2x, and then now the capacity of PCM in like not single level cell mode but quad level cell mode is 8 gigabytes. And now we need to compute the write latency of our new PCM. So now, since the endurance is increased by a factor of 10, we know that the number of writes we need to send for each cell is like 10 times 10 to the 7, which was the previous value. Now it's 10 to the 8. And then the memory capacity is reduced by 4 because compared to this one, because we are storing 1 bit instead of 2 bits in one cell, and like 2 bits means like 4 values. So it's like the capacity is going to be the capacity here over 4. And then the required number of writes is going to be this times 1 over 2 to the 9 as we calculated above because of the 64 byte granularity of the writes. And then we know that, like, let's say this value is X, the write latency is like 8 plus 13, which is like the time it requires from like to send a memory request from the CPU to memory controller and memory controller to PCM, and plus the X value that we want to find. And then the new lifetime of this PCM cells is equal to the previous one times 2, which is 2 times 10 to the 7. Now we need to just solve for this equation again, which is 2 times 10 to the 17 equals to this capacity over 2 to the 11 times 10 to the 8, which is like the number of writes, plus the latency. And we know this one to be 8 gigabytes. And then if we solve for the X in this equation, it's going to be something like 2 to the 12 times 10 to the 9 over 8 times 10 to the 9 times 8 minus 21. Okay, any questions? Okay, so now this is like the last part. And then here we have like a resistive memory. We store one matrix in this resistive memory, and we have some inputs and we have some outputs, but we don't know one of the inputs, we don't know one of the outputs, and we don't know one value of the matrix. And it explains how in general this mechanism works. So we convert this
Okay, so this question is asymmetric multicore. Let's go over it. A microprocessor manufacturer asks you to design a multi-core processor for modern workloads. You should optimize it, assuming a workload with 60% of its work in the parallel portion and 40% in the serial portion. You're asked to compare two configurations that can fit into the processor's die area. First one is a small cores, SC, and the second one is large plus small cores, which would be LSC. So these two configurations consist of following. So SC is a design that contains 8 small cores which share the same die. 7 of these small cores operate at the baseline fixed instruction throughput, but the 8th small core is an overclockable core which can operate at either the baseline throughput or the overclocked scenario with 2 times the baseline throughput. And LSC is a design that contains 1 large core and 4 small cores that all share the same die. The 4 small cores operate at the baseline throughput, and the large core is 4 times faster than the small ones. Okay, in addition, table 1 provides the static power for when the core is idle and the dynamic power for when the core is active for each of these cores. So we see here, let's take a look at the table. For small cores, we have the 2 cases, baseline and overclocked. And then we have this large core. So it covers all the cases. We'll get back to this table when we need it. The SC processor, the first configuration, executes the parallel portion on all small cores, including the overclockable core operating at the baseline throughput. So that is when we have the parallel portion. And for the serial portion, it only works on that overclockable core. But then based on the power budget we have, we can decide, should it be baseline config of it or the overclocked config of it. So that was for SC. Basically, this is a little bit important. Let us then underline it. So the SC processor executes on all the small cores and the serial portion only on the overclockable core using either baseline or overclockable options. And the LSC processor executes the parallel portion only on the small cores and serial portion only on the large core. So, okay, these guys go only on the small one and the serial portion only on the large core. So these are important to remember. Okay. Which of these following three configurations, SC and SC with overclocked core, or SC results in the highest performance, and show your work. Okay, let's see how that will work. And then remember, 60% of our application is happening in the parallel portion. So for finding the speed up, let's say, so here, for SC, or where is the eraser? Okay, so speed up for SC scenario would be something like this. 1, so the serial portion, it would run on the that one core. So we would just have divided by 1. So it's no way of accelerating it here. And for the parallel section, we have this divided by 8. So with here we can see, okay, 3, so simplify it, 3 here, 40, that will be something like this. Okay, so now let's go to the SC with overclock. So the speed up would be again 1. Here, how much was this faster? Overclock 2 times. Okay, and the parallel part does not change. Okay, we want to do simplification here. Maybe, or I can cheat alternatively. Here. And this one. So here we have that big core that was 4 times faster. So now everything's going to be fast in this case. But for here, we only have this 4 cores. And if we do calculations, so this would be kind of like 1 here will be 4. But then since we want to compare to other things, instead of writing 4, we can write this. So we would see that this one is having the best performance because it's having the highest speed up. This config. Okay, now let's go see what happens next. So we did some analysis for performance. Now I want to do some analysis for the energy consumption because it should be also a metric of reference in your design. Which of the 3 design configurations, SC with overclock core or LSC, result in the lowest energy consumption? Show your work. So here we have the power values. So we need to see how much of the time is spent in whatever configuration. So we would multiply the time by power to have some analysis of energy in that case. Let's go remember some things. So here, when the small cores are idle, they have this much static power. When they're active, this value. So maybe I can have the paper version of it here in front of me so that because an iPad is a little bit difficult to switch the pages in this case, but remember somehow these values. Okay. So when we want to find the total energy, we need to find the energy spent on the serial portion and energy spent on the parallel portion. So we know the ratio of time spent on the serial portion and the parallel portion in these parts, right? For example, here, 0.6 divided by 8, let's say, could be the parallel part, whereas relatively 0.4 could be the serial part. So if you have the paper, you can like flip it easily and check it and quickly do the calculations in this case. So let's find energy consumption for the serial case. Okay, sorry, for the SC case. When we are doing the serial portion of that application, we have that core, the normal core, which is in this baseline config, using 1. Here, that's the power. But the 7 other cores, they are idle, right? So then we would have this case. So how much of the time was spent on the serial part? 0.4. So I do this one a little bit like in more detail than the other ones would be a lot more clear, right? And when we do the dynamic part, all the cores are active, so all 8 of them are going to use 1. And how much was the amount of time spent on this part? It was, let's say, 3 multiplied by 40, divided by 40, right? Basically this number. Okay. So let me quickly go for the SC overclockable scenario. So the overclockable one makes this part faster relatively, right? Because it's twice as fast. So, and we have here, let's go one by one. Okay, when it is, again, we have these things idle, and the power is 8. Okay. Now let's go. When this overclocked one is idle, it is no, sorry, because now it is acting just like a normal core for the parallel section. So we just do 8 multiplied by 1. And the ratio of time spent on the parallel section, again, is the same here, as you see. Okay. Let's see what happens here. So in this part, we have this thing running this bigger core, 4 plus, but we had 4 small cores in this case. So we have 4 multiplied by 5, 0.5, and this would be 1.10, sorry, 0.1. Okay. And here, this thing, when it is static 2 plus those 4 things being active, right? Those 4 cores use 1, and the time they take is this. It should be. Okay, so now in this phase, again, I cheat so that we go a little bit faster, but these calculations are very small, very easy, as you see, it's like really round numbers. So quickly we find these. Okay, which one is consuming smallest amount of energy? It would be this one relative to the other 2. Okay, now let's see. So the question is asking at least what ratio of a workload should be spent on the parallel section so that the SC configuration, even without overclocking, performs better than the LSC configuration. Show your work. So the SC configuration had a lot of small cores, whereas the LSC configuration had a bulky core to accelerate the serial portion of the application. So for the parallel portion, we would have a smaller number of cores relatively. And we want to see that how big should the parallel portion of the application be? Yes. Mm-hmm.
So like energy is equal to power times time.
Mm-hmm.
And so like if you're using 0.4 as the time, is the actual time or is that like the relative time? So these energies, like that's not actual energy in watts or joules. It's like 2.4 times some constant.
Yeah, it's relative. Yeah, because you are doing, we are basically finding relative times in that case. Okay. So for this part, yeah, basically we want to see how big the parallel portion of the application should be for us to have a C configuration in our system instead of LSC. So let's just have a parameterized scenario. So if we have, let's call the parallel portion of our application P. So what we want is that 1 minus P divided by 1 plus parallel portion divided by 8. So this is speed up. We want it to be bigger than 1 minus P divided by 4, because that was what the larger core was doing. And then P would be 4. So then we do a little bit of calculations. 1 minus P plus P8 here, 1 minus P. So these things go away with each other. So here we have 1 minus 7/8 of P less than, I mean, right, 1/4. Am I being correct? 8, oh no. Here, so wait. Okay, I'm having elementary school issues right now, which we will resolve. So here we have, and let's multiply everywhere for 8. Okay, so these guys went away. We have here 2. We multiply these things by 8, so this is P. Okay, so let's bring 7P here and 6, right? Oh, I did it correctly. Right, so yeah, it's a stage fright. Otherwise, I would say I do these much faster. So, okay, in order to improve the performance of the LSC configuration, so, okay, we realized here that if our application is really parallel, the LSC configuration actually does not perform really well. Then we think, okay, let's improve its performance. What can we do? So in order to improve the performance of the LSC configuration, we come up with hardware design optimizations to improve the throughput of this large core. And we expect that these optimizations will increase the throughput of the large core by T times. So we improve this, and we want to see, okay, if your application is really parallel, let's say it has 90% of its work in the parallel section, can we actually have LSC configuration to outperform the SC configuration with overclocking? And if yes, how much should we speed up our core? Okay, then this is like very simple again. It just needs, after this point, just some arithmetic simple operations to be done. So how we want the speed up for SC with overclocking to be smaller than the speed up of LSC configuration, right? Here, then that means we would have one. So here we have 1/10. 1/10 of it is 2 times here, divided by 8, correct? This should be smaller than 1. Okay, we had already 4 times it was faster. Then we multiply it by t plus 0.9. This part does not become faster. Then again, whoops, sorry. And again, we do some small things. Okay, it is, let's make everything 80. Okay, 4 divided by 80 plus 9 divided by 80. And here I would have 2 divided by 80t plus 18 divided by 80, right? So this thing goes away from here and there. And in the end, let me see. So this thing, somehow 13 should be more than 2t plus 18, right? Which means that 13. So wait, actually, we don't need to do some more. This just doesn't happen, right? It just wouldn't work for any positive value of t. So the question was, is it possible? No, it's not possible. Yeah. Then, questions?
So we are going to be soon run out of time, but I'm going to quickly also discuss this question, the interconnection networks. So in this question, we have 16 processors, and we are connecting them in 2 different topologies. The first one is for mesh, and the second one is TROS. So I guess you are aware of these 2 topologies from Professor Mutlu's lectures. So we are going to design some routing algorithms for these 2 topologies. In order to define routing algorithms, we define them based on the turns that they are prohibited for packets to take. So we can have 8 different turns in a 2D mesh or 2D TROS network. So if you consider clockwise, we can have north-east. Yeah. We can have northeast, east, south, southwest, and west-north turns. And for counterclockwise also, we have 4 different turns as well. So here we have 3 routing algorithms. The first one, we are saying that turns northeast, southwest, northwest, and southeast are forbidden. The others 4 turns are allowed. So the easy way to understand this routing algorithm is to understand the basically concept of this routing. So when we don't have north-east turn, and when we don't have, let's say, southwest, it means that it's impossible that we go in Y direction and then we want to turn to X, right? Also for the counterclockwise terms, when we don't have northwest and southeast, it is impossible that we go in Y direction and then take X. So which means that this routing algorithm is simply XY routing or dimension order routing. So for the routing algorithm 2, only 2 terms are forbidden. Terms southwest and northwest. So southwest is from in the clockwise circle, we don't have southwest. And in the counterclockwise circle, we don't have northwest term. So here also, you can imagine how this routing algorithm looks like. So I don't know why it's not good. Okay. So when we don't have southwest and northwest, it means that it's impossible that we go south or west, sorry, south or north, and then we want to turn to west. In other words, if our destination is in the west of the network, we first need to go completely west. And at some point, when we are done with the west part, we can go north or south. But if the destination in the east of the network, then basically you can do whatever you want. So this routing algorithm, meaning that if the destination from west, so to west, it is actually, you can consider it as XY routing. But if you are going to east, the routing is actually fully adaptive. Is that clear? Okay. And the third routing algorithm turns west north and north west are forbidden. So west north here and north west. So this one is a bit hard to deal with, I mean, to understand what does it look like. Basically, in order to understand it, you just need to make sure that you don't take these terms. I'm not going to interfere this routing algorithm to any of easy, understandable routing algorithm. Okay. So the first part, we are going to basically write some paths. So we have 2 different source destination pairs from processor 5 to processor 11. Oh, also recall that these routing algorithms, they should be minimal routing. Do you know what does it mean, minimal routing algorithm? Which means that we need to take the minimal number of hops from the source to the destination. It is important actually to consider. Okay. So basically here, what we want to say for 2D mesh network, for example, if we want to go from processor 5 to processor 11 using algorithm 1, basically what should be the path? So we already know that algorithm 1 is XY routing. So processor 5 to 11, the path should be P5, P6, P7, and P11. Okay, sounds easy. I'm going to skip the next one also. So for algorithm 2, P5 to P11. So P5 to P11. So P11 is in the east part compared to P5, right? So we can basically go there in a fully adaptive way. So what are the different paths? One pass is P5, P6, P7, P11. The other pass could be P5, P6, P10, and then P11. And another pass could be P5, P9, P10, P11. These are the only three minimal passes that we can take. However, for the second one, which is P5 to P12, P5 to P12, because P12 is in the west part, I mean, with respect to P5, we need to consider only dimension order routing. So we go P5, P4, P8, and P12. Is that clear? Okay. So let's also do one for algorithm 3. P5 to P11. I'm also going to cheat. Okay. Yeah. So P5 to P11, the only thing we need to be worried about is taking turns west-north and north-west. So since P5 to P11, we are actually going to the east part of the network, right? So it's completely fully adaptive. So the answer would be the same as the routing algorithm 2. However, from P5 to P12, which is the second part of this question, since we are going to the west of the network, we may take west-north or north-west. Are we really taking those terms? No, because P12 is actually, with respect to P5, is in the south of the network. So if you want to go minimal pass, basically, you won't take any west-north or north-west passes. Okay, sounds good. So for the torus is a bit, I would say a bit harder. So for the first one, P5 to P11, we can, again, we can have this P5, P6, P7, and P11 again. But there should be also another way. We can go this way. Basically P5, P4, and then take the wraparound link to P7, and then go south. P5, P6. For the first algorithm, no, because the first algorithm is XY, right? So we cannot take east-south turn, right? Because no, we can take actually east-south turn, but we cannot take south-east, because in the end you need to also take a southeast turn, right? That is forbidden. Okay. So I'm not going to explain more for the first part of this question, because I guess you can see them from the solution. Yeah. I mean, the hardest part for this 2D throws, if I remember correctly, was this P5 to P11, that we have 6 different passes. So, and I remember that many students, they just wrote 2 or 3 passes or 4 passes, so they couldn't be comprehensive enough for this one. Okay. So the next part of this question is about deadlock free. So I guess you're all aware of the deadlock. Basically, whenever you have some circular dependence in your network and packets cannot be proceed anymore, we are in deadlock position. So We are asking that basically for each topology and each routing algorithm, you need to prove that it is deadlock free or deadlock can happen. So if if the algorithm is deadlock free, you need to prove it. Or if you are saying that this algorithm is not deadlock free, you just need to provide an example that deadlock can happen. So for the routing algorithm 1, we know that it is XY. From the course, also, you know that XY is deadlock free. But if you want to basically prove that also, that would be easy. Let's take a look at this. So usually, if you want to prove that an algorithm is deadlock free, we can use contradiction. So we consider that we have deadlock. If we have a deadlock, so it means that we have a circle. And that circle could be clockwise or counterclockwise, right? Consider that, I mean, without loss of generality, we can consider that circle is clockwise. So if the circle is clockwise, there should be the rightmost link, right? Not link, I mean, the rightmost edge of this circle. So if you have the rightmost edge, at some point, you should have some turn from west to south and south to east, because the rightmost edge, there should be some turn like this. Do you agree? So in algorithm 1, we don't have we don't have south. We don't have southwest, right? So southwest is forbidden, which means that we cannot have that rightmost edge in a clockwise orders. And for the counterclockwise order also is similar. You just need to consider the leftmost edge. Is that clear for you? Okay. Any? Okay. Yeah. I mean, the answer, if you write something like that, would be enough. But if you want me to explain more. So basically, let's see, actually. I guess after explanation of routing algorithms 3, that would be more clear because, no, I can explain also here. Okay, so whenever we have a deadlock, it means that there are some packets that they are waiting for each other. For example, P1, processor P1 is sending packet to P3. Processor 3 is sending packet to P6, for example. Sorry, processor 1 is sending to P3. P2 is sending to, for example, P7. P3 wants also to send something to P6. P7 is sending to P5. And for example, P5 is sending to P2. I mean, there should be a circular, accesses. And you should also know that the probability of that deadlock is not that high but when we are saying that this algorithm is deadlock free, which means that it is impossible that deadlock happen. But some algorithms, deadlock can happen with some probability. So if all of these transactions, which I mentioned here, all the packets, they are injected at the same time together, then we would have deadlock. So you see that I'm thinking of circular accesses. So whenever you have a circular request, it means that there should be some packets that they are taking the rightmost edge. If we are thinking of clockwise circle. I mean, for the counterclockwise is also the proof is the same. So yeah, for the clockwise, there should be the rightmost edge. And for the rightmost edge, for sure, some packets needs to take east-south turn, and some packet is also taking south-west turn. Otherwise, we wouldn't have that circular, right? So since in routing algorithm 1, we don't have south-west turn, then for sure we don't have this turn. Which means that we cannot have the rightmost link. And then the contradiction is false. It's clear now? Okay. So for the routing algorithm 2, the proof is exactly the same because we cannot have, again, southwest turn. Okay. So you're using the southwest turn for proving that the deadlock cannot happen in clockwise order, and northwest for counterclockwise. Okay. Here we can, for counterclockwise, we can also consider the rightmost link, rightmost edge in that circle. Okay, and that's all. So for routing algorithm 3, actually, so that was also the hardest part, I would say. The deadlock can happen. So here I'm providing an example that, so there are 8 packets with the following sources and destination. P1 is sending to P6. Cannot show them together. So P1 is sending to P6. Yeah, P1 to P6. P2 to P5. Basically, I'm considering how many hops between them, like 3 hops, right? So P1 wants to send to P6, P2 to P5, P5 to P8. I mean, the circle of this, let me explain it a bit differently because it's a bit hard. Now I understand why this question was hard, actually. Okay, no, I'm just kidding. So for the routing algorithm 3, turns west-north and north-west are forbidden. So if you pay attention to the proof that I provide just before, I was thinking of rightmost link, rightmost edge, and to not happen. So here, since we can have actually in the counterclockwise, in the clockwise, we can have the rightmost edge, right? Because both east-south and southwest are allowed. So we can have that. But for the counterclockwise, west-north is So northwest is forbidden. So for the counterclockwise, we cannot have the rightmost edge. But the thing is that the combination of the allowed link that we have, they can make a circle. You know, here, if you check this one, actually we have this figure in the lecture. Because of that, actually, we designed it like that. But by the way, so we can have this turn, and then this turn is also allowed. This turn is also allowed. But then you don't need to go up, because go up is forbidden. But you can continue and then go down, and then turn to east, and turn up to north, and then you made a circle. So the circle in routing algorithm 3 is a bit complex, but can happen because the combination of the terms that they are allowed, they can make a circle. Yeah, because we had that picture in the lecture, because otherwise, I mean, yes, I agree. But yeah, anyway, I mean, this semester interconnect question would be much easier. Yeah, don't worry about that. Okay. Sure. So, yeah, because I mean, there is no, for a specific routing algorithm 2, because the terms that they are forbidden is southwest and northwest, and they are contributing to the basically rightmost edge. No, I'm considering that because I want to make a proof, right? I'm saying that if we have a circle, I mean, that's the hint, right? From the terms that they are forbidden. So since here, southwest and northwest are forbidden, I can see that they are in the rightmost part. But for example, for XY, because northeast and southeast are also forbidden, you can prove with the leftmost edge. Okay. So, so the answer for Trost network is actually very easy because all of them has deadlock. So in Trost network, we have topology has a circle, right? So if we have only use also XY routing, consider that in this example, let me actually find the, yeah. So yeah, consider that P0 wants to send to P2, P0 to P2, P1 to P3, and then P2 to P0, okay? And P3 to P1. These 4 packets, they make a circle. Even though we have XY routing, because the topology has a circle, all of them, they can wait for each other and provide deadlock. And since XY has deadlock, for sure routing algorithm 2 has deadlock as well, because routing algorithm 2 is less constrained compared to routing algorithm 1. And for routing algorithm 3, since we already proved that it has deadlock in mesh, then for sure for Trost is also has deadlock. Okay. And the last part of this question is basically you want to select an appropriate routing algorithm for your topology, which could be mesh or Trost. So the constraint that you want is that the routing algorithm should be deadlock free and also should not be deterministic. What does deterministic mean? The routing algorithm which is deterministic means that it always takes this, there is only one pass from the source to the destination. So for the 2D mesh, there are 2 algorithms that they are deadlock free, routing algorithm 1 and 2. The routing algorithm 1, because it's XY routing, we know that XY is deterministic routing because no matter about which source and destination you're selecting, there should be only one pass. Okay, so routing algorithm 1 is deadlock free, but deterministic. However, routing algorithm 2, we know that if we want to go to the east part of the network, we can make it considered as a fully adaptive. So there are, which can utilize the path diversity. So basically the answer would be routing algorithm 2 for the mesh network. And for the Trost network, basically none of them, because none of them are deadlock free. For throws, yes. Basically, I guess in Professor Mutlu's lecture, you learned that one of the job for virtual channels is to also avoid deadlock. So we can add virtual channels to the topology, to the network, and break the deadlock cycle. The other way is that make it more constrained. So for these three algorithms that I mentioned, the constraints are not enough to avoid deadlock. But if there are some actually risk papers in the past that they show that if we add more constraint to Toros, I mean, to the routing algorithm, which is for Toros, we can make it also deadlock free. But you don't need to, I mean, know them basically. If you are interested, you can send me an email and I will share with you some material. Yeah. Okay, that's all. But yeah, for sure, this semester interconnect question would be easier. So don't worry much about this one. Okay, thanks a lot. I think we are done. Yeah, and wish you all the best for the exam next Thursday.
Okay, we can go to the prefetching question, which is the bonus. It's the last one. I mean, it doesn't matter that it's a bonus because you will get the points anyways if you solve it. So there's no point of. So this is also a qualitative question. There's no calculations that need to be done. You're designing a hardware prefetcher for a processor using reinforcement learning. If that brings something to your mind, there was a paper discussed during the course, which is called Pythia, published in Micro 2020 or 21. 21, I think. 21. And for a memory request to the cache line address A, the prefetcher selects a prefetch offset 0, O, let's say, and issues a prefetch memory request to the cache line address A plus O to the offset. For every prefetch request, the memory hierarchy provides a numerical award R to the prefetcher that can take a value of the following three reward levels. Accurate, signifying that the prefetch request was demanded by the processor indeed. Inaccurate, signifying that the prefetch request was not demanded by the processor. No prefetch, signifying that the prefetcher did not prefetch anything. In the initial configuration of the prefetcher, you set the values of the reward levels as follows. R equals 20, R in minus 4, R in P minus 10. What does that mean? If we do an accurate prefetch, we give a reward back. We say, okay, you did well. If you have an invalid prefetch, inaccurate prefetch, then you reduce the score. And if you have a no prefetch, we are even more aggressive. We're like, why did you not prefetch? You need to prefetch. Recall that the coverage of a prefetcher is defined as the fraction of a program's memory request correctly prefetched by the prefetcher. So coverage means that we have a bunch of memory requests and the prefetcher issues many things, many requests, or more than the memory requests that happen in the system, and we were able to cover the whole working set size of the application, a large part of the working set size of the application. And the accuracy, what does that mean? We prefetched something and it was indeed used. So the accuracy is a different metric from the coverage. We might have probably we have a really high coverage, we also have a high accuracy. But we might have a small coverage, but then also a high accuracy. There is a correlation, but it's not exactly the same thing. This is also defined in your lecture, I think, for the prefetching lecture. So let's go to the questions. Which of the following statements, if any, are correct if you set the reward for not prefetching to 1000 in the initial prefetcher configurations, given that all the other values, except no prefetching, remain the same as the initial configuration? And there might be multiple choices which are correct here. First, the coverage of the prefetcher will significantly increase. The coverage of the prefetcher will significantly decrease. The prefetcher will start prefetching aggressively, and the accuracy of the prefetcher may increase. So, if we give a reward to a no prefetch action, like we have three actions, right? We have two actions basically, either prefetch or not prefetch, right? We do not prefetch, and we give a reward of 1000 compared to -4 and 20 for a no prefetch. Then which of these would happen? Is there a chance, for example, that we will have a higher coverage by prefetching less? If we give a higher reward for not prefetching, this means that our prefetcher will learn that, okay, if you don't prefetch, we're fine. Prefetch less, for sure. Is there a chance that the coverage will be higher? No, there is no chance that this will happen. Is there a chance that the coverage will significantly decrease? Yes, because we will prefetch less. We told the prefetcher, you didn't do a good job, not prefetching was the best thing, so the coverage will decrease. The prefetcher will start prefetching aggressively. That's not possible because we're giving a feedback to the prefetcher that we're telling the prefetcher, hey, don't prefetch, and that's really good. And the last one, the accuracy of the prefetcher may increase. This is something you cannot be sure about, but it may indeed increase because you will prefetch less and your coverage might be less, but the requests you might send might be more accurate, right? You're not sure about this. So it's B and D, the correct answers to these ones, because A and C are not possible. Does anyone have any questions on that? I guess it's quite simple, this one. Which of the following statements, if any, are correct? If you set the inaccurate prefetch to minus 500, so you have the inaccurate prefetch to minus 500, the no prefetch to minus 10, and the accurate prefetch to 20. Again, we need to do the same thing. So let's try to answer this here. So let's see. The prefetcher will aggressively prefetch even though the prefetches might be inaccurate. Is that possible? No. Why? Because we're telling the system, hey, you did inaccurate prefetches and I'm gonna punish you for that, minus 500 points for Gryffindor. So it's like you cannot prefetch anymore inaccurately, and there is no chance that the prefetches which are inaccurate will be issued more. Why? Because the prefetcher is instructed not to prefetch aggressively. So A cannot be the case. The accuracy of the prefetcher will likely increase. Yes, the accuracy might increase because we're punishing a lot the inaccurate prefetching. So B, so the accuracy of the prefetcher will likely decrease. No, because we punish the inaccurate prefetches. There's no way that the accuracy will decrease. And the third one, the coverage of the prefetcher might increase or decrease. Are we sure about this? No. So it's possible. So there is a chance that the coverage might increase or decrease. If we punish inaccurate prefetches, probably the prefetcher will learn to prefetch more accurately, right? There is a chance that the coverage might increase based on that or decrease. So again, the correct answers are B and D. And the last question, you want to make the prefetcher system aware by incorporating into the decision-making process the type of power source used in the system. And you want to configure the prefetcher in the following way. The prefetcher should generate accurate prefetches whenever is possible, irrespective of whether the system is connected to an external power adapter or running on a battery. So if this is the case, which R value should be the highest? If we always want to be the most accurate possible, yes, which R value? Correct. So RA, which I cannot write on the right part, is the correct one and needs to be the highest of all because we always want super accurate prefetches, right? So if the system is connected to an external power adapter, the prefetcher should continue to prefetch even if the prefetch might be inaccurate. So if this is the case, which one should it be in the second branch here in the LSIV, where we have the external adapter? Which one should be higher, the no prefetch or the inaccurate prefetch? Correct. Why? Because even though we might be inaccurate, we will prefetch aggressively because we do not care about not prefetching. We want to prefetch as aggressively as possible. And if the system is running on battery, the prefetcher should prefer not to generate a prefetch request if the prefetch is likely to be inaccurate. So in this scenario, we do not want at all inaccurate prefetches. We want super accurate, as stated in the beginning. We want no prefetches, our next choice, and then we want the inaccurate ones, right? So the order would be here, it would be the accurate, then it would be the no prefetching, and then the inaccurate ones. Okay, sorry for not being able to write, but I think you understand the solutions. And if someone has a question, we can discuss it later and I can show you the full answer if you want. Okay.
Okay, thanks a lot, Konstantinos. I think we can have a
Let's have a break to fix the.
yes, 10 minutes break.